Welcome to another ASA Operator Academy webinar. Today's webinar is Understanding Basic Access Control Technology. My name is Russell Corriveau and I will be your lead instructor today. This session will last about 50 minutes, give or take 10 minutes. And during this session, your lines will be muted. However, you can pose questions as we go along using the question and answer icon at the bottom of the page. And we will reserve time at the end for your questions. This session is being recorded and will be available for viewing within 24 hours. Also within 24 hours, you will receive an email from ASA Operator Academy as your proof of attendance to this webinar that can be submitted to your employer or one of the industry association partners, such as DHI or ALOA for industry CEUs in lieu of a certificate of completion for these short trainings. In addition, ASA Operator Academy has over 50 online courses that are all available at no cost. To get started, simply just create an ASA Operator Academy account and begin learning at your own pace. So now for access control. Okay, safety is always first to ASA Operator. Always make sure you're wearing the correct equipment before you do any type of installation. So what are we going to be talking about today? We're going to be talking about what is access control? How do locks communicate? How is access granted? 125 kilohertz versus 13.56 megahertz. Encryption. How do cards communicate? And what is parity? What is access control? Access control is the ability to restrict access or the ability to obtain desire or information. So it's controlling information or locations. Electronic access control means to control access electronically to one thing or another. We're going to be discussing electromechanical access control in reference to door locks. In recent history, access control has been handled by mechanical locks, such as exit devices, mortise locks, cylindrical locks, and deadbolts. But with so many advances in wireless technology and electromechanical locks, many options have become available. And that's what we're going to look at today, some of the different options. But it's good to take a look at some basic terms that you should be familiar with. Okay, the first term we're going to go over is local area network. Is a collection of computers or other network devices within a single physical network. The modem allows the local area network to connect to the internet. Items within a local area network include items such as routers, desktop computers, laptops, cameras, and printers. An example of a local area network could be all the computers or devices in a single department or in a single building. A Wi-Fi router is wired to the modem, which allows the Wi-Fi router to access the internet. The Wi-Fi router will broadcast a Wi-Fi signal to allow wireless devices such as laptops to connect to the internet. The Wi-Fi router will also have ports which will allow wired devices such as desktops to connect to the internet also. A wireless access point is a device that creates a wireless local area network. It is wired to the router using an Ethernet cable and produces a Wi-Fi signal in a designated area. A wireless access point is, in its standard default mode, relays data between the wired network and the wireless devices. Multiple wireless access points can be wired to the same router to access the internet. Large organizations will use wireless access points throughout the building to allow the same Wi-Fi signal to be used throughout the building. With wireless access points, if changes need to be made to the network, the IT manager can make changes to the entire network by logging into the one router. If the wireless access points were replaced with routers, the system would remain fully functional. The issue would be is that the IT manager would now have to log into every single router to make changes to the entire network. So wireless access points is the way to go. A wireless access point in the client mode, there are different modes when it comes to wireless access points. In the client mode, It relays data between a wired network and wireless devices. In the client mode, the access point once again creates a local area network, but is connected wirelessly to a router or to another access point opposed to being wired. Okay. A protocol is a set of rules governing the way in which computers communicate with each other and other devices. An IP address is short for Internet Protocol Address, which is used to identify computers on the internet. IPv4 is a 32-bit address, such as 25.241.19.92. Each set of 3 digits will range from 0 to 255. With IPv4, protocol limits the number of devices that can connect to the internet to just 4,294,967,296 devices. So you are limited to the number of devices, and obviously there's a lot more people than that in the world. Okay. How would this IP address be written in binary? This IP address is more correctly written as 025.421.019.092. This is a 32-bit address. This is a 32-bit IP address. It's 4 sets of numbers ranging from 0 to 255. 32-bit means that the system can only handle a 32-bit binary number. So what's a 32-bit binary number? The IP address written above is written in binary and is specified as the first 8 digits is equal to 25 in base 10. The second 8 digits is equal to 241 in base 10, and the third set of 8 digits is equal to 19 in base 10, and the last 8 digits represent 092 in base 10. This is a 32-bit binary number, okay? And 25.241.019.092 is the IP address in base 10. Other than that, it's going to be 32 digits that we showed you. Note that the binary IP address is made up of 32 digits of either 1 or 0, and they're broken up into 4 groups of 8. Each group of 8 will represent 3 numbers in a base 10 number ranging from 2 to 55. In binary, the location of the digit represents a value. Let's look at a 2-bit binary number. Remember, a 2-bit binary number is made up of 2 digits, either 0 or 1. So this gives you the option of having 0, 0. And the way this is calculated is it's going to be 2 times 0 plus 1 times 0 is equal to 0. 0, 1, that's going to be 2 times 0 is 0. 1 times 1 equals 1, so we have a total of 1 there. 1, 0 in binary numbers is equivalent to 2, and that's 2 times 1 plus 1 times 0 is 2. And 1, 1 in binary is actually equivalent to 3. So it's 2 times 1 plus 1 times 1 is for a total of 3. So with a 2-bit binary number, only 4 numbers are available: 0, 1, 2, 3, 1, 2, and 3. With an 8-bit binary number, there are 8 digits, either 1 or 0. With 8 zeros, it calculates out this way. As I said, each location represents a number. So at the 8th location, that's going to be either a 1 or a 0 times 128. In the 7th location, it's either going to be a 1 or a 0 times 64, plus the next location is 32 times 1 or 0, plus 16 times 1 or 0. So if our binary number is 8 zeros, our final result would be 0. So that's going to be our first number. That's going to be our lowest number. If we had 8 ones in this binary number, that's going to be calculated as 128 times 1 plus 64 times 1 plus 32 times 1 plus 16 times 1 plus 8 times 1 plus 4 times 1 plus 2 times 1 plus 1 times 1 for a total of 255. And that's the reason why the numbers will range from 0 to 255. With an 8-digit binary code, the largest number you can produce is 255. So with an 8-bit binary code, 256 numbers are available, ranging from 0 to 255. An IP4 address is a 32-bit address, consisting of 4 sets of 8 bits. As I'm sure you're familiar with, the IP address 192.168.0.1. Most of us have all heard of that, especially when we set up our own wireless local area network. This is a private IP address, and this is normally used by router manufacturers as a default IP address. As we just talked about, with IPv4, the number of devices that can connect to the internet is just over 4 billion. And due to this limitations, network address translation was developed. Let's take a look.
NAT stands for Network Address Translation, and this is a service that is used in routers. And its purpose is to translate a set of IP addresses to another set of IP addresses. And the reason for having the NAT service is to help preserve the limited amount of IP version 4 public IP addresses that we have available around the world. Now, there are 2 different types of IP version 4 addresses. There's public and there is private. Public IP addresses are publicly registered on the internet. You have to have a public IP address if you want to go on the internet. And there are approximately 4 billion public IP addresses available, so they are limited. Now, private IP addresses are different. Private IP addresses are not publicly registered, so you cannot directly access the internet with a private IP. Private IP addresses are only used internally, such as inside a home or business. They are not used out on the public internet. And your router is what assigns your internal devices a private IP. Now, you could contact your internet service provider and ask them for these additional public IP addresses for all of your devices, but that's going to be more expensive, unnecessary, and more importantly, it would also be a waste of public IP addresses. And let's face it, if every device in the world had their own public IP address, we would have ran out of public IP addresses already. So instead, we can have our router assign the devices inside our home or business private IP addresses. And when our devices need to access the internet, their private IP address will be translated by NAT in the router to the one public IP address that we have been given. So not only does it translate private to public, but it also translates public to private. Because if a computer out on the internet wants to communicate with a computer on this private network, then the public IP address needs to be translated by NAT to the private IP address for that computer.
Okay. Since IPv4 limits the number of devices that can connect to the internet to just over 4 billion, due to these limitations, IPv6 is being rolled out. IPv6 is a 128-bit address, which allows up to this many devices, I can't say the number, but this number of devices to connect to the internet at one time. An example of a IPv6 address would be something like this: 2305:2080EB:2089:F8A9:G653:4AA6. And you're probably asking yourself, we just talked about binary, how do you handle letters? Well, that has been handled by the American Standard Code Information Exchange, and they have their own chart so you can convert letters into binary numbers. Okay, classifications of IP addresses. IP addresses are either going to be static or dynamic. Either static or dynamic. With a dynamic IP address, a new IP address is provided by the internet service provider to the device every time it connects to the internet. With a static IP address, the address never changes and is a permanent internet address. Domain name system servers is a static IP address. The DNS, or domain name system protocol, is an important part of the internet's infrastructure, and it serves as the internet's phone book. Your computer performs a DNS every time it looks up a website, every time you search for a website on your computer. A few more terms you should be familiar with that's used in access control would be a request to exit switch. A request to exit switch is a switch that informs the access control system that a contact has either been opened or closed. This is usually used to shunt an alarm. A request to exit switch may be mounted on the wall. It could be incorporated into the lock or the exit device. So as you rotate the inside lever handle or push on the push bar, the contact is either opened or closed, shunting the alarm of the access control system. Without a request to exit switch, when the door is open, the access control system will assume that the door is being forced open from the exterior. So shunt time. The shunt time occurs when an access control system receives a signal from a request to exit. When the signal is received, the access control system will shunt or prevent the alarm from sounding, recognizing the signal from the request to exit switch as being an authorized egress or ingress. If the signal is not received from the request to exit switch and the door is open, the door position switch, DPS, will inform the access control system that an unauthorized egress or ingress has taken place. Those of you who may not be familiar with a door position switch is used to determine the status of the door as either being opened or closed. Shown to the right is a typical door position switch. The portion with the wires is usually installed in the frame, and the other portion contains the reed switch, and that's installed in the door. Okay. I'm sorry, I said that wrong. So shown at the right is a typical door position switch. The portion with the wires is usually installed in the frame and contains the reed switch. The other half of the door position switch is installed in the door itself and contains the magnet to activate the reed switch. A reed switch within a door position switch is either opened or closed by bringing a magnet in proximity to the switch. So when the door closes, the switch is either opened or closed, and when the door is open, the status of the switch changes, indicating a change in the status of the door. Occasionally, door position switches will be installed on the edge of the door just above the lock. In these cases, the portion with the wires would be wired directly into the lock, and now the frame will contain the magnet opposed to the other way around. A passive infrared reader is a device that uses infrared energy to detect motion within an area. A PIR, or passive infrared reader, can be used as a request to exit switch to shunt an alarm. They are also used with low energy operators to verify that the coast is clear before a low energy operator opens up a door. A couple other terms: open architecture. Open architecture components are capable of supporting multiple access control technologies and integrate with multiple non-proprietary network processors, controllers, and integrated locking hardware, card readers, and third-party applications. Closed architecture. In a closed architecture environment, the hardware manufacturer chooses the components to be used with their products, and generally they cannot be updated with non-proprietary products. In 1997, the Institute of Electrical and Electronic Engineers, IEEE, created the first wireless local area network standard. They called it 802.11 after the name of the group formed to oversee its development. Wi-Fi is a frequency within the electromagnetic spectrum. The electromagnetic spectrum is the entire range of waves or frequencies within of electromagnetic radiation, extending from gamma rays to radio waves, and includes visible light. Electromagnetic radiation is made up of pulses of energies. The wave determines the frequency and is measured in hertz, or cycles per second. Electromagnetic waves can travel through air, they can travel through solid material, and they can actually travel through the vacuum of space. They do not require any medium for travel, such as sound waves do. Here's a quick look at the various frequencies and where they're used. Here we have visible light. Just to the right of the visible light, we have ultraviolet light, followed by diagnostic radiation such as X-rays and gamma rays. Just to the left of the visible light, you have microwaves, which range from 3 to 30 gigahertz, followed by Wi-Fi, which is a 2.4 gigahertz or 5 gigahertz, followed by cellular phones, then broadcast TV, radio waves, FM, and then ending up with computers and power lines. Did you ever wonder how is electromagnetic radiation created? We know it comes from the sun in different areas, but how do you create it? Let's take a look. Because if you've ever wondered how electromagnetic frequencies are created, here's a quick look at how the first electromagnetic frequency was created.
In the modern world, we humans are completely surrounded by electromagnetic radiation. Have you ever thought of the physics behind these traveling electromagnetic waves? The great scientist, Heinrich Hertz, was the first man to transmit and detect electromagnetic waves. In his famous experiment, a high-voltage current was applied to the two ends of two metal wires, which generated a spark in the gap between them. This spark resulted in the radiation of electromagnetic waves. Those electromagnetic waves traveled through the air and created a spark in a metal coil located over a meter away. If you had placed an LED in that gap, the bulb would have glowed. This was a clear case of electromagnetic wave propagation and detection.
Looking at the Wi-Fi frequencies, 802.11 is an unregulated radio frequency of 2.4 gigahertz with a bandwidth of up to 11 megabytes per second. 802.11a is a regulated radio frequency about 5 gigahertz and supports bandwidths up to 54 megabytes per second. Okay, let's talk about Wi-Fi security for a few minutes. Wi-Fi security, encrypted communication and delivery. WEEP was the original security on Wi-Fi. WEEP meant wired equivalent privacy. This was the original encryption standard for wireless communication. The card payment or the credit card industry actually prohibited use of this in 2008 because it was no longer secure. So what was developed was WPA or WPA2, which is Wi-Fi protected access. This was developed to correct the errors with WEP. And it is as secure as the password used. So the more complicated password, the more secure this encryption is. Next, we're going to take a look at how do locks communicate with the access control system or the head end. Traditional online access control solutions. Traditional solutions, electromechanical hardware is required to be hardwired for communication and power. Typically, non-proprietary products are used in the access control locks, signaling, monitoring. This is ideal for high security application or very complex electrified opening. Usually requires the access control panel and interface panels, which are going to be located above the ceiling. So this was the original where everything was hardwired into the door and everything needed to be wired up. So it took a lot of time to install, a lot of wires being run through the door and such. Our next option is power over Ethernet. Power over Ethernet, or PoE, is a technology which allows wired devices such as locks, wireless access points, cameras, and IP phones to be powered over Ethernet cables within a local area network. The PoE Ethernet transmits electronic power along with data to remote devices with a standard twisted Ethernet cable. such as Cat5 or Cat6 within a local area network. So the PoE cables carry both power and data, so it's a single wire run. PoE, power over Ethernet locking solutions, offer a simplified solution with a simple wire run for both power and data. A PoE switch is a computer network device that powers and connects network PoE devices such as locks and cameras to the network. That's all a network switch is. The original PoE supplied 15.4 watts of current, which is equivalent to 0.64 amps at 24 volts. PoE Plus supplies 25.5 watts of current, which is more than 1 amp at 24 volts. Both standards supply enough power to operate Sargent and Corbin Russwin's PoE locks. The current enters the cable by means of a component called an injector or a switch. Some of the advantages with PoE locks include the use of standard twisted cables, such as Cat5, Cat6, and Cat7 for locking and power, for lock power and data. Centralized lock management, which means you can lock down, you can control everything from a single location. Real-time door status monitoring and alarm reporting. So as someone goes through that door, it's picked up by the access control system. So that's what they mean by real-time. True lockdown capabilities. Since everything is wired directly to the access control system, the access control system can do a full lockdown on all the locks and then immediately lock everything. You can also use dual credential with these as long as they have a keypad, and it's a great alternative to traditional hard wiring with new construction. Our next technology we're going to look at is called Apereo.
Apereo is a smart solution that offers several advantages to the security-minded and budget-stretched. First, it is truly easy to implement. Installing access control usually requires expensive and complex wiring around the door opening, and in many cases, doesn't allow for non-traditional applications like cabinets and drawers. With Apereo, wireless technology eliminates the wiring to the lock, making Apereo a fast and affordable way to add access control anywhere. Apereo hubs come in a variety of configurations to ensure easy integration with your existing access control systems. The IP Apereo hub uses standard Ethernet cabling to connect to IP access control systems and supports up to 16 devices per hub. The RS-485 hub connects to an RS-485 access control panel and supports up to 8 locks per hub. The Mercury-powered hub connects to any Mercury-powered controller and supports up to 8 locks per hub. The Wiegand hub connects to industry-standard Wiegand access control systems and can support a single lock. Because Apereo leverages existing access control infrastructure, bringing security deeper into the facility and to different applications is a breeze. Simply add Apereo wireless locks and an Apereo hub to update and monitor openings in real time. Available in a variety of form factors, Apereo makes it possible to add access control to applications where audit trail and monitoring are becoming increasingly critical.
With Apereo hubs, the lock communicates wirelessly to the Apereo hub at 2.4 gigahertz. The Apereo hub is connected to the access control system, either using IP hubs, RS-485, Wiegand, or Mercury wiring. As I mentioned in the video, the RS-485 hub allows up to 16 devices to a single RS-485 hub wirelessly. For security, there is encryption for the radio communication, and the hubs has an integrated antenna and LEDs for visual status. The best way of communicating for RS-485 is with a daisy chain laid out with the controller at one end. With communication distance of up to 4,000 feet, which RS-485 is notorious for, very long distances, traveling distance of up to 4,000 feet, and a RS-485 extender, you can communicate very, very long distance, and you can have actually up to 32 devices in a daisy chain configuration, which is quite a bit. The IP hub connects the access control system via IP or Ethernet connections. The IP hub allows up to 64 Apereo devices to a single hub. The hub contains an integrated antenna with the option of an external antenna, and the radio communication is encrypted. The IP hub is powered by the Ethernet connection, or you can also have it hard-wired separately other than the Ethernet cable. The Imperial locks are available with a wide variety of applications, including commercial, metal and wood doors, glass doors, aluminum doors, in addition to cabinet locks and servers. For these applications, the Imperial locks are available as mortise locks, cylindrical locks, exit devices, cabinet locks, as well as electric strikes. Did you ever wonder why twisted wires are better than standard wires? With standard wires, the wires are in parallel to each other. The noise created by the electromagnetic spectrum affects the information being transmitted through the wires, and since the wires are running parallel, the electromagnetic spectrum affects them slightly differently. When the wires are twisted, the noise created by the electromagnetic spectrum affects each of the wires equally, and therefore having a less effect on the transmission, on the information being transmitted. And that's why we always suggest twisted wires, because the electromagnetic waves will affect them equally. Next, and this is actually probably the very best, Wi-Fi access control. IP-enabled Wi-Fi locks use the existing Wi-Fi infrastructure. With Wi-Fi locks, the locks communicate wirelessly to the access point, which is hardwired to the network, completely eliminating any electronic access control infrastructure. These locks talk directly to the same Wi-Fi that your computer does or your laptop does. Advantages with the Wi-Fi locks: there's no wiring through the door or through the frame. It's utilizing existing 802.11b and G wireless access points. Near online centralized lock management. Battery powered, easy to install because they are battery powered. Hardwiring is possible if you need lockdown capabilities. Keep in mind, when you have a battery operated lock, it contacts the head end system periodically. That's called a heartbeat, and you can set the heartbeat on how often you want it to contact the head end system. So if you have a heartbeat of 10 seconds within a lock, the fastest you can do a lockdown capability would be 10 seconds. That would be the slowest. So as soon as you set down the lockdown, if the communication occurred at that point, they would lock down immediately. But if right after it sent out a signal, if you had to wait 10 seconds, it could take up to 10 seconds to do a lockdown capability. It does have real-time alarm reporting, and what that means is that if someone tries to break through the lock will wake up automatically and contact the head-end system to let them know that there's a problem. Here are some of the access control partners and IP-enabled products. Just realize, Osable has been working with a lot of different access control companies, so our products can be used with their different access control systems. A little bit more on Wi-Fi technology. Shown here is the evolution of the Wi-Fi standard for 2.4 gigahertz versus 5 gigahertz. Over the years, the capacity to carry more information has greatly expanded. In 1997, the bit rate was only 2 megabytes, which is equivalent to 2 million bytes of information per second. In 2013, the bit rate increased to more than 1 gigabyte, which is more than 1 billion bytes per second, and continues to increase. 2.4 gigahertz offers 3 non-overlapping channels of the 11 channels available. 2.4 gigahertz bandwidth is prone to interference. Many household items, such as Bluetooth devices, cordless phones, microwaves will affect the quality of a 2.4 gigahertz signal. Wi-Fi 5 gigahertz. At 5 gigahertz, the airwaves are far less congested. There are 23 non-overlapping channels, and 5 gigahertz offers considerably higher bit rates. One of the disadvantages with the 5 gigahertz is due to its higher frequency, the signal cannot travel nearly as far as a 2.4 gigahertz. 5 gigahertz actually offers 8 times the bandwidth of a 2.4 gigahertz with little interference from other devices. So here's a quick comparison. With 2.4 gigahertz, some of the advantages are the signal can go further and it can penetrate solid objects better than 5 gigahertz. Some of the disadvantages, it's vulnerable to interference because it is not regulated and it does have slower speeds. 5 gigahertz has higher transfer rates. You can transfer more information quicker and is less vulnerable to interference because it's on a regulated frequency. The big disadvantage is you have shorter range and it has a harder time penetrating solid objects. So if the airwaves are clear, you'll have no problems, but there's a lot of cement walls and such in between that could cause a problem with the signal traveling through the walls. Okay, integrated Wiegand access control. Integrated Wiegand is an open architectural platform and is compatible with the most popular access control systems. Integrated Wiegand system requires only one cable run from the lock to the access control panel. Industry standard Wiegand output eliminates the need for any additional interface panels or controllers. So what is Wiegand? The Wiegand effect is a nonlinear magnetic effect produced through a special manufacturing process. During the manufacturing process to create the Wiegand effect, the wires are twisted and untwisted to cold work the outside shell, and the wire while retaining a soft core on the inside of the wire. And then the wire is aged. This process makes the Wiegand card virtually counterfeit-proof. When the Wiegand card is brought in range of a proximity reader, the Wiegand wire suddenly reverse pulses and generates a sharp uniform pulse, which are read by the readers. The set of wires contain data such as access codes, credit card numbers, employee IDs, and more. So how is access granted? Before proximity technology, mag stripes or mag swipes, or called swipe cards, were read by swiping them through a card reader. The credential was unencrypted, making the cards less secure than today's access control technology. One big advantage with the magnetic strip cards is that the card needed to be physically obtained to be able to read or to clone the data. Proximity technology changed everything. In times with the limitations of swipe technology began to be felt, the need for physical contact between the reader and the credential could be cumbersome and inefficient for users, while broken cards and physical wear to the readers became costly and time-consuming for administrators. Thus, the emergence of contactless technology was a game changer in the access control industry. The predominant technology at the time was known as PROX, also known as low frequency PROX. It operates at 125 kilohertz of data on the 125 kilohertz. The data on the card is detected by presenting it within a few inches of a reader. The proximity credentials are available in many forms such as PROX cards, fobs, and tags. Simply presenting the credential within range of a proximity reader will activate the Wiegand effect within the card. The Wiegand effect produces a uniform pulse, which are read by the Wiegand reader as ones or zeros. This is a good visual on how a proximity or RFT reader and the credential interact. The proximity reader creates a magnetic field, and when the credential is brought within the magnetic field, the credential responds to the magnetic field to produce a uniform volt pulse, which are read as ones and zeros. The proximity reader interprets the credential and then grants or denies access. The uniform volt pulse created by the credential is known as the Wiegand effect. Okay, let's look at some of the differences between 125 kilohertz PROX cards and 13.56 smart cards. At the turn of the century, contactless smart cards emerged and offered even more sophisticated than PROX cards, more sophisticated technology than PROX cards. These smart cards included brands like MyFair and iClass, utilizing high-frequency technology at 13.56 megahertz and features new credentials. Shown are the locations of the frequencies within the electromagnetic spectrum. They reside within the radio waves portion of the spectrum. The Wi-Fi communication occurs at 2.4 gigahertz or 5 gigahertz. Next, we have the proximity cards, which communicate at 125 kilohertz. And now we have smart cards that communicate at 13.56 megahertz. And lastly, at 900 megahertz, you have the frequency that was frequently used in the past with cordless phones within people's houses. First, we'll take a look at 125 PROX cards. What is inside of a 125 PROX card? 125 PROX cards are embedded with a microchip and an antenna. The microchip embedded within the card has only one function, which is to provide a proximity reader with the card's identification number and/or site code number. This information will be used to determine if access is granted or not.
A PROX reader is normally connected to a controller with from 4 to 6 wires, using a topology known as Wiegand protocol. Wiegand protocol has 4 essential wires, 2 for power and 2 for data. Other wires may be connected to furnish LED, beeper, or parking control. Shown here is a typical PROX card. Within this card is a small chip and antenna. The chip is only the size of a portion of your fingernail. By making the antenna smaller, the credential can take other forms, such as a tag, key fob, or printable ISO card. Stored within this chip is a short binary expression known as a format. It is the format that provides the identity of the cardholder. The reader is constantly putting out low-frequency, low-energy bursts 10 times per second. When the credential gets close enough to the reader, this energy will power the chip within the credential, and the credential will send the format to the reader. The reader will convert the RF signal into Wiegand protocol and send the format to the controller, which will then make a decision whether or not to unlock the door.
The most common technology used today is 125 kilohertz PROX. It was introduced almost 30 years ago. These contactless cards were extraordinarily reliable and lasted a real long time because there were no batteries to fail. The proximity card relied on the radio frequency broadcasted from the reader, which is really nice. What are the limitations? 125 PROX is transmitted in the clear, which means the information is not encrypted, making it susceptible to modern day attacks such as sniffing and cloning. 125 PROX cards are easy to clone without the card readers even being aware of it. 125 PROX cards lack the additional features of more advanced card technologies, such as two-way communication, memory, processing power to handle applications. PROX cards cannot be encoded with multiple IDs or data attributes. Now for 13.56 megahertz.
Smart cards have a small integrated circuit inside a credit card-sized plastic card. Contact-type smart cards must be inserted into a reader in order to work. I-class technology, like proximity, is contactless and provides the user with the freedom of presenting the card within a few inches of the reader. I-class cards and readers offer several unique features that put it a step ahead of traditional RFID technology. These features include cryptographic data storage, mutual authentication, secure reading and writing of data, and user-definable access keys.
A 13.56 megahertz contactless smart card is essentially a miniature computer on the card. It has a microprocessor, it has memory, it has software programs, security, and more. The smart card's address has the smart card addresses two major limitations of PROX cards. First, mutual authentication. Both credentials, the credential and the reader, have encrypted keys in them. When the credential is first presented to the readers, the two use a complex mathematical process to compare the keys. If the keys match, the credential will be shared, and if the keys match, the credential shares the binary data with the reader, and the reader will accept it as genuine. However, if the keys do not match, the credential will not be shared, and therefore the transaction will be terminated. Secondly, these cards can store more information than just an ID number, such as cashless spending, biometric templates. 13.56 was a substantial increase in both security and functionality.
I-class readers install identically as PROX readers using Wiegand protocol if desired. The credentials are available in the same forms as PROX credentials. Just like with PROX, the format resides within the chip on the card, but there is a difference. I-class communicates on a higher frequency, which enables bidirectional and faster communication. This enables the format to be secured. Like PROX, the I-class credential is powered by the reader. With I-class, however, when the credential is presented, a dialogue takes place between the credential and reader known as mutual authentication. It is called mutual authentication because the reader authenticates the credential and the credential authenticates the reader. This process takes about 1/10 of a second, and when completed satisfactorily, the format travels to the reader over RF and to the controller using Wiegand protocol. I-class security is transparent and requires no configuration. Credentials are issued identically and the controller is configured no differently than if it were connected to a PROX reader.
13.56 megahertz read-write contactless smart card technology provides high-speed, reliable communication with high data integrity. Two of the brands available is I-class technology, which is 13.56 megahertz card technology, ensuring high security and mutual authentication and encrypted data, and 64-bit diverse keying for read-write capacity. The second brand is MyFair technology, which is also 13.56, but is factory programmed with a unique 32-bit serial number. It was originally developed to handle payment transactions for public transportation systems in Europe. However, nowadays it's used for access control. The dangers, despite these benefits, is most first-generation smart cards have vulnerabilities in mutual authentication algorithms that have been exposed by researchers and have been published. So we came up with the next generation of credential technology. The second generation of credential technology of contactless smart cards, such as Seos and MyFair DesFire EV3, was introduced to meet the needs of business. The second generation of contactless smart cards differ from their predecessors in two areas: security and application. In terms of security, proprietary protocols that were more vulnerable than the first generation cards are no longer used. Second generation credentials also offer enhanced privacy protection and feature standards approved by research and academic communities such as ISO and NIST. These open standards are consistently being updated and adjusted, enabling them to be leveraged across multiple technologies, allowing organizations to create and manage secure identities not just on cards, but on cellular phones, tablets, wearables, and other credentials connected through NFC, Bluetooth, or other communication protocols. HID came out with Security Identity Object. This is a cryptographically protected data model for storage and transporting data information as a single object. The data within the SIO is secured with a wrapper that is provided with which provided a diversification key, verified signatures, and encryption. SIO can be deployed on a number of form factors, including contactless and contact smart cards, smartphones, USB tokens, and provides a layer of security independent of the device itself. So this is an additional layer of security.
Every organization has a need for access control. In the beginning, this was achieved with physical keys. After that, technology evolved into swipe cards. Then, HID Global made the leap to contactless technologies. And we continue innovating to meet the demands of our modern world. Today, we are doing just that by offering best-in-class security, unrivaled mobility, and applications beyond traditional access control. Introducing Seos, the next generation of credential technology.
Seos is a software-based credential technology, so it's not tied into an underlying hardware chip. This independence creates a wealth of opportunities to extend this security credential technology into a much wider variety of form factors and communication protocols. Seos can be ported on different microprocessors for the ability to deliver multi-form factors. Security teams can issue mixed smart cards and mobile devices to meet the employee's preferences. The Seos provides a flexibility to select communication protocols and presents a consistent interface with the access control reader, regardless of the communication method. Additionally, HID access control, HID mobile access, employees can use their smart cards to access doors, gates, networks, and more, so it can be used for multiple applications. The other nice advantage is that software patches can be deployed over the internet if needed, as opposed to having to reissue card-based credentials.
Physical access control is critical to security. Nothing new there. But today, many organizations are still using outdated access control systems. The problem? These systems can be rigid and leave your organization open to unnecessary vulnerabilities. Introducing Seos, the next generation of credential technology from HID Global. What's different about Seos? With best-in-class mutual authentication and cryptography based on open standards, Seos is more secure than other credential technologies and offers unrivaled data and privacy protection. And Seos is software-based, so you're free to choose the right mix of form factors for your unique needs. For example, use mobile devices to open parking gates, wearables to access restricted areas, and smart cards to unlock PCs, whichever mix is ideal for your organization. What's more, Seos can be extended for unique applications beyond physical access, like cashless vending, secure print release, network login, and other custom applications for a variety of industries. Seos, the next generation of credential technology that provides the ideal mix of security and flexibility for any organization. Learn more about how you can take your access control to the next level with
Seos is the first virtually fully secure 128-bit encrypted software-based credential. Seos is capable of being loaded on most smart devices. Seos is also being used in a number of mobile applications such as hotel chains, cloud-based logic access control, and physical access control. Seos credentials can be put on cards, they can be put on smartphones, they can be put on smart watches, and Seos will work with any HID, I-Class SE, or multiple class SE access control readers, revision E or newer. Seos is compatible with many ASA APLOY access control, Seos is also compatible with many ASA APLOY locks and accessories. A couple limitations on this is limited read-write range. So you need to bring the card within an inch or two of the reader. Increased reading time, so it does take a little bit more time for it to read the card. No slots are available on the cards or the technology. And limited third-party support at this time, but it's expanding. I know this webinar is run a little bit longer, so if you do need to get off, I do understand. I am going to continue on for those of you who might be interested. I do have a quick question here. So, may the phone be used for parking access and computers, or does Seos have to be a separate device? No, it does not have to be a separate device. It can be programmed onto your phone, and that can also be used to access printers, the network, and other devices like that. So it does not require a separate device. So I'm going to continue on with a little bit more of this. I understand if you want to get off, if you need to do something else, but we're going to be covering a few more things that you may find interesting. Okay, So next thing we're going to talk about, and I thought this was very interesting the first time I saw it, is we're going to take a look at what it takes to build a credential. Shown is a page from the HID website that goes over the options available for the various credentials. First, we're going to take a look at the available styles. If you're not familiar with the offering, a comparison chart is available through the hyperlink. Our first option is printable cards, which are available in single or multiple technologies. Next, we have key fobs, which are only available with a single technology, but includes a slot so you can put it on a keychain. Next, we have adhesive tags, and it can be applied to a plastic ID card and turn that plastic ID card into a smart card. Once again, only a single technology. And our last style is a clamshell. Once again, this is only available in a single technology, but comes in a sturdy case for industrial applications. Once the style has been selected, now it's time to select the technology. Once again, HID offers a hyperlink to a chart comparing the various technologies that are available and what can be paired with what. And this is the chart here. For our credential, we're just going to select a printable card. We're going to choose I-class Seos, 125 PROX, and a mag stripe. The nice advantage with the printable cards is that they're available for multiple technologies. Then all you have to do is hit next. As we discussed, I-class technology includes a memory. So the size of the memory needs to be selected. Smaller memory sizes are typically used to provide a cost-effective way of utilizing the desired technology of your access control installation. Larger memory sizes have more space to enable more applications and supports further growth. Take notice that there is no memory option for 125 kilohertz PROX because there is no memory in that, as we discussed previously. For our credential, we're going to choose two different types of technology: I-class Seos and HID PROX. Now it's decide if you want the technologies programmed. Unprogrammed is the default for both, but let's look at the options. Our first credential is the I-class Seos, and we want it programmed. It will be programmed with the secure identity objective. Don't forget, that's going to take all the information, gather it into one single thing, and transmit it that way. Next, you need to select your credential data privacy, either high, medium, or low. And this is going to have to do with what's written on the cards. So high privacy is going to have no numbers written on the card at all. Medium privacy will have numbers on the cards with non-matching numbers on a printed sheet elsewhere, so you can actually match them up. And then the lowest privacy, the numbers on the lowest privacy is numbered with the matching printed number on the card, so things match. Our second credential is the HID PROX, and which we are going to want programmed as an HID PROX format. Once again, the credential data privacy needs to be selected as either high, medium, or low. Since the two credentials are going to be programmed onto the card, now it's time to select the programming format for each of the credentials. You have 4 different choices: good, better, best, and custom. Once again, there's a hyperlink to supply a breakdown of the three types of formats. First, we have good, which is standard. It's effective in most industry standards. It's compatible with most system and contains a facility code and a card number range. Our next choice is better, which is 37 bits. This is a managed format and compatible with most systems. The managed format ensures that there are no duplications ever created. This 37-bit offers a range of over 34 billion unique, never duplicated numbers. And for our last one, we have the best, which is corporate 1000. That's a 48-bit, and its managed and controlled format is compatible with most systems, and the credentials are never duplicated. Once you've chosen the security level, there are a few more questions on what you want written on the cards. Next, we have the key set. Next, we have the key set to be selected. The options are HID Elite or Standard. HID Elite security program supports unique key sets per site and company basis. The Standard security program provides a universal key set that offers maximum compatibility with card readers and matching security for the general public. And lastly, after you've gone through all those steps, you can get a PDF of everything you just specified. Okay, just a few more things really quick. The evolution of credentials. So back in the 1990s, we had PROX 125. That's over 30 years old, and it had no encryption, and it's very easy to copy, and it's low frequency, 125 PROX. Then in 2002 and 1996, and this is about 20 years old, we had simple shared key security. High frequency was 13.56. And then we came out with the second generation, which was secured with 125-bit encrypted security identity object, which transmits all the information as a single item. The hardware-dependent communication and security. And lastly, we have Seos, which is a 128-bit software-based credential. The next subject we're going to touch on quickly is encryption, and I thought you might find this interesting. We just discussed encryption as a major advantage of 13.56 over 125 kilohertz, which is not encrypted. Now we're going to take a look at what encryption is. An algorithm is a formula to solve a problem based on conducting a sequence of specified actions. The algorithm is what is used to encrypt the information. Okay, the first type of encryption we're going to look at is symmetrical encryption. You have a credential such as 5645 and an encryption key. The encryption key is used to encrypt the credential, and the encryption is an unknown value. The encrypted information is what's sent over the internet. Okay, so the encrypted information is sent over the internet, and once the encrypted information reaches its final destination, the encryption key is used to decipher the encrypted information to determine what the original credential is. This is symmetrical encryption because symmetrical encryption uses the same key for encryption as well as unencrypting the credential. Asymmetrical encryption works similar to how email works. With asymmetrical encryption, an individual must have a public key, which is like an email address. The public key is accessible to the public if they know what your public key is, similar to how your email address. Anybody can send you an email as long as they have your email address, but they cannot access your email account without the password. The encryption on the public key is the password. The strength of the encryption is determined by the password and how complicated it is. The more complicated the password, the better the encryption. When the information is sent across the internet, it is sent to the public key. The information can only be read with the correct public key and the corresponding password. And our last type of encryption is hashing. Did you ever wonder why Gmail, Hotmail, or other websites that require a password to access them will never give you a password when you request it? The reason why they won't give you a password, the reason the password is not given, because Gmail, Hotmail, and similar sites, they don't know what your password is. They'll offer to reset your password because of the encryption type that's used, and that's hashing. This is how a company handles your password without ever knowing what your password is. With hashing, your password is run through an algorithm to produce a password which is recognized by the company as your password. The original password and the password produced through the algorithm are completely unrelated, and since the hashing algorithm is unknown, there is no way to determine what your password is from the password created by the algorithm. In this example, the password is 12345, and when the password is sent through the algorithm, it can be recognized by the company as this password. So every time the password is entered, it is run through the algorithm to produce the same password recognized by the company. If the password entered is incorrect and is put through the algorithm, the information produced by the algorithm is going to be completely unrelated and will not be recognized will not be recognized as your password by the company, and therefore will not allow access to the information or the account. And this is why companies will reset your password, but they will not provide your password because they don't know what it is. Okay. How are we doing? There's still 8 of you out there. Don't forget, I'm going to continue. I have 2 more sections. You can stay with me if you're interested, or you can drop off. I know I'm running long, but for those of you who are interested, let's talk about how cards communicate. Okay. How does a card communicate? A format describes what the number means and how the number is used. The format is not the number itself. For example, a 34-bit format may have an 8-bit facility code, while another 34-bit format may have a 12-bit facility code. For example, there are over 100 different 34-bit formats alone. Within a given bit length, 34-bit, 37-bit, the size and the location of the data elements may change. The capacity of the access control system will dictate the formats that will and will not work. So your access control system is going to tell you what formats you can use on your cards or your credentials. Okay, the format describes what the number means and how the number is used. The format is the structure of the data, stored on the access control credential. The number of ones and zeros and how they're put together determines the format and ultimately the credential number. The card format is identical for 125 PROX and 13.56 megahertz I-class cards. This ensures that any controller capable of understanding a 125 PROX card will also understand a 13.56 megahertz card. This is a standard layout for a 26-bit card. The 26-bit supplies over 16 million combinations. The standard 26-bit format has an 8-bit facility code and a 16-bit ID number. Notice the even and the odd parity. We'll talk about them in a few moments. The standard 26-bit format is an open format. The 8-bit facility code provides 256 possibilities, while the 16-bit card number offers over 65 unique card numbers. The open format means that anybody can buy these cards, unlike the corporate 1000 and the 37-bit cards. The 26-bit format is widely used as the industry standards and is accepted by most access control systems. 37-bit provides an open format to the industry while simultaneously assuring that the numbers are unique and will not be duplicated. Under this format, HID controls and issues the credential numbers and does not duplicate any of the numbers. The corporate 1000 is a 35-bit format designed to provide larger end users with their own proprietary format. This ensures that their credentials will not be duplicated because HID reserves these exclusive corporate 1000 formats for these end users. And our last subject is parity. This is the 26-bit format the format for a 26-bit card. The leading and the trailing bits are security features. The 26-bit series consists of 24 bits of data plus a leading and a trailing parity. The leading parity will be set to generate an even parity for the first 13 bits transmitted. Since there are 6 ones in the first 13 bits, which is an even number, and since the leading parity must be set to 1 or 0, so the total number of ones is an even number, and since we have 6 ones, and the leading parity must be 0, and this identifies that there are no errors in the first 13 bits. Okay, so the leading parity has to be even, and since we have 6 ones, that means our leading parity is going to be 0. And since they do have 0 in there, that means it is correct. The trailing parity is set to generate an odd parity for the last 13 bits. Since there are 5 ones in the last 13 bits, which is an odd number, and since the trailing bit is set to 1 or 0, so the total number of ones is an odd number, the trailing parity is set to 1, which identifies that the 13 bits are correct and identifies that there are no errors. If the trailing bit was 0, we would have only 4 ones, which is even. And since the trailing bit must be set to produce an odd number of ones, the 0 would identify that there was an error in the card and it must be reread. Okay. Either the leading or the trailing parity is not correct, the information is incomplete, and the card must be reread or represented. This is a security feature to detect errors as the information is being transmitted. In this example, you have 6 ones in the first 13 bits, and the leading parity is set to 1 or 0 to produce an even parity. The leading bit should be 0, which it is not, and therefore it identifies that we have a problem. For the second 13 bits, there are 5 ones, and since the trailing parity must be set to produce an odd number of ones, the trailing parity must be set to 0, which it is, and it is correct. Okay. So with a 26-bit format, the 24 bits of data remaining, 8-bit for the site code and 16 bits for the user code. And that finally brings us to the end of our presentation. I appreciate you guys hanging in here, or all of you ladies and gentlemen hanging in here for the rest of the presentation. Hopefully you found it worthwhile, and I hope you had a great day. I am going to stay here in case there are any questions. But if not, thank you very much for your time. Stay healthy and have a great day. Thank you. Great. There appears to be no questions. Thank you very much and have a great day, everyone. Bye-bye.